To make this a little bit clearer, let us take the same example but work through it under the situation where n is equal to 3, which means that the t values must be in the range 0, 1 or 2. And over here arbitrarily I am going to assume t of a1 is equal to 0 and t of a2 is equal to 2. What are the possible choices? T of a1 equal to 0, t of a2 equal to 1 would also be valid. a1 equal to 1, a2 equal to 2 would be valid, right? But a1 equal to 0, a2 equal to 0 is still not going to be valid. a1 equal to 1, a2 equal to 0 or 1 is not valid, for example, right? Or at least as things stand over here, they are not, those are not valid implementations. So with this, what do we get? The df value now becomes the time of a2 minus the end of a1, right, plus w into n, which in this case is 2 minus 0 plus 1 plus 0, or in other words it is equal to 1. And if I want to draw the equivalent hardware architecture, it essentially says it will look like this adder, right. So now there are three choices out here. Okay, and I now need to decide what happens at each time. T of a1 is 0, so a of n and b of n need to be made available as inputs to the adder at time 0. Okay, there is no operation at time 1, therefore there are no inputs to be given to the adder at that time. And at time 2, what I have is c of n to be provided here, and this output of the adder to be provided, but now because df was equal to 1, I need to delay it further by 1 register. And if you work through the steps, time instance 0, 1, 2, 3, 4, 5, 6, and compute the phase of the clock, right. So the phase of the clock is essentially what I am referring to over here. It is either in phase 0 or phase 1 or phase 2, then goes back to 0, 1, 2, 0, 1, 2, 0, 1, 2 cyclically. So depending on the phase of the clock, I will essentially get different inputs being applied to the inputs, or different values being applied to the inputs of the adder, and each of them correspondingly are implementing one of the operations in the data flow graph. So that is where this df essentially becomes useful. All that it tells us is we can automate this process of figuring out how many registers to put when we are taking a particular output and connecting it to the appropriate input. Okay. Just to round this off, we will take one further example before going on to a more complex example, which will be useful finally. I am going to take the same a1, a2, but now I am going to say I am pipelining this, put a delay element on it. So this basically says that w is equal to 1. Now again let us go back to, or let us just continue working with n equal to 3. Now interestingly, I can choose any other value of t of a1, and just to sort of see how to do things, I am going to choose t of a1 equal to 1, t of a2 equal to 0, and let us see what happens to the df value now. Df equals t of a2 minus t of a1 plus pa plus w times n. This is equal to 0 minus 1 plus 1, normally this would not have been acceptable, plus 1 into 3. The fact that there was that sample delay, one iteration delay, basically means that now the df has become positive, right. So it is 0 minus 2 plus 3 equal to plus 1. Okay. What does my hardware architecture look like? I have an adder. Now I know that t of a1 is equal to 1, which means that I can straight away say from there a of n and b of n must be fed to the 1 inputs of the corresponding switches or multiplexers. And what about T of A2? It is 0, right? So in other words, the A2 operation is going to happen during phase 0. C of n can be applied over here, and this output can be fed in, but there is a df equal to 1. And if you work through the time steps corresponding to this, the main thing that you need to note over here is because of this sample delay, right, the output produced by A0 is something that would have been consumed by A1 of 0 would have been consumed normally by A2 of minus 1. So A1 of 1 is what is going to be required by A2 of 0. Okay, sorry, the other way around, right? So A2 of 0 is going to use something that was generated one iteration earlier, A1 of minus 1. A2 of 1 will be using A1 of 0, A2 of 2 will be using A1 of 1, and so on. Okay. So if we write out the time sequence saying these are the time instants at which the different A of n, B of n, C of n values are being generated and applied over here, right, correspondingly everything will change. Of course, you need to keep one thing in mind. I arbitrarily did one pipelining step over here, that is to say I inserted one iteration delay between A1 and A2. Okay. But keep in mind that if I am actually doing pipelining, what do I need to do? I need to make sure that since my original graph looked like this, if I am actually doing a pipelining, I need to keep in mind that in principle, even though I am not marking them, these are also nodes as far as the system is concerned, which means that a proper pipelining will have to be like this. If I insert a delay element over here, I also need to insert one delay here, so that the C gets delayed appropriately by one clock cycle before it is being applied to the input. When I draw the data flow graph, that detail gets hidden away because I am not treating my sources as separate nodes. So in other words, these kind of things, when you are actually implementing them, you need to apply your mind and make sure that you are doing it correctly. The pipelining step that you use is valid and that you have delayed all the inputs appropriately so that you get the correct output. As long as you take care of that, the approach itself will work.